Hello, my friend. Tonight, we're stepping into one of the most powerful and mysterious phenomena in the universe. Objects so bright they can outshine entire galaxies, yet born around something completely dark. Quasars may look like tiny distant lights, but they are among the most important cosmic objects ever discovered because they reveal how black holes grow, how galaxies change, and how the early universe once looked. They are ancient, extreme, and filled with clues about parts of reality we still do not fully understand. And the deeper you go into their story, the more it begins to feel as though the universe has been quietly hiding something enormous in plain sight. So if you've had trouble falling asleep, you're in exactly the right place. Get comfortable, let the day fall away, and together we'll drift toward the brightest monsters in the universe. Chapter 1. What a quasar really is. To understand a quasar is to stand at one of the most exciting edges of modern astronomy, because these distant lights show us how gravity, matter, and cosmic history can combine into something so powerful that it can outshine an entire galaxy. A quasar is not a star, even though it first appears to be one. It is not a planet, not a nebula, and not a simple cloud of gas shining in the dark. A quasar is the intensely bright central region of a galaxy whose supermassive black hole is actively feeding on surrounding matter. That is the simplest correct description. If you remember only one idea from this chapter, let it be that a quasar is the bright, active heart of a galaxy, powered by material falling toward an enormous black hole. That description may sound strange at first, because black holes are famous for being dark. By definition, a black hole is a region where gravity has become so strong that once anything crosses a certain boundary, not even light can escape. So how can something connected to a black hole become one of the brightest things in the universe? The answer is one of the most beautiful pieces of physics in astronomy. The black hole itself is dark, but the material around it is not. Gas, dust, and sometimes even whole stars can be pulled inward by the black hole's gravity. Before that matter disappears forever, it forms a rapidly rotating structure around the black hole called an accretion disk. Inside that disk, particles crash into one another, rub against one another, heat up, and release enormous amounts of energy as light and other forms of radiation. The light comes from the hot falling matter, not from the black hole itself. This is why a quasar is best imagined not as a hole in space that glows, but as a gigantic cosmic engine. At the center sits the black hole, silent and invisible. Around it spins a disk of infalling matter, compressed and heated to extreme temperatures. The closer the material moves toward the center, the faster it travels and the more violently it interacts. Gravity is doing the work. Matter loses orbital energy, spirals inward, and that lost energy is converted into heat and radiation. In a way, a quasar is a place where gravity is turned into light. The black holes that power quasars are not small objects left behind by ordinary stars. They are supermassive black holes, the largest class known, with masses millions or billions of times greater than the mass of the Sun. Many galaxies, including our own Milky Way, contain a supermassive black hole at their center. But not every galactic center is a quasar. The difference is activity. A supermassive black hole becomes part of a quasar only when large amounts of matter are actively falling toward it. If the black hole is quiet, with little material feeding it, then the galaxy may look ordinary. If fresh gas is driven inward, the center can flare into extraordinary brightness. So a quasar is not a separate kind of object floating alone in space. It is a phase in the life of a galaxy, a period when the central black hole is feeding with great intensity. This helps explain why quasars were so confusing when astronomers first found them. In telescopes, many of them looked like tiny points of light, much more like stars than galaxies. That is reflected in the name itself, which grew out of an older phrase meaning a star-like source. A normal galaxy often appears as a broad island of stars with visible shape and structure. A quasar can be so bright in its central region that the rest of its host galaxy becomes difficult to see. The glare of the active center overwhelms the softer light around it. From very far away, all that reaches us is a point-like beacon, almost like a lighthouse seen across an ocean at night. That point-like appearance does not mean a quasar is small in every sense. The region producing much of the light is much smaller than an entire galaxy, but the phenomenon itself is tied to a galaxy-sized system. There is a host galaxy around the quasar, filled with stars, gas, dust, and dark matter like other large galaxies. The quasar is the active nucleus at the center. So when we say a quasar can outshine its galaxy, we mean the energy released near the black hole can exceed the combined light of all the stars in that galaxy. Billions of stars, each blazing through nuclear fusion, can be visually overshadowed by the activity of matter falling into one central region. At first, this seems almost impossible. We are used to thinking of stars as the great light makers of the universe. Stars shine by nuclear fusion in their cores, turning lighter elements into heavier ones and releasing energy in the process. Quasars do not work that way. Their brilliance is driven mainly by gravitational energy released as matter falls inward and heats up. This is one reason quasars can become so unbelievably luminous. They are not just bright by the standards of a single star. They are bright on the scale of entire galaxies. Another important idea is that quasars are usually very distant. When astronomers study them, they are often looking across enormous stretches of space, which also means they are looking back in time. Light does not travel instantly. It needs time to cross the cosmos. So a quasar seen from very far away is not being observed as it is now, but as it was long ago, sometimes when the universe was much younger. Because of this, quasars are not only dramatic objects in their own right. They are also historical messengers. They carry information from earlier chapters of cosmic history. This is one reason quasars matter so much to astronomy. They are not just strange lights to classify and admire. They help scientists understand how the early universe evolved, how supermassive black holes grew, and how galaxies changed over time. Some of the most distant quasars known were already shining when the universe was still relatively young. That creates a major scientific puzzle. If supermassive black holes need time to grow, how did some of them become so enormous so early? Even the existence of distant quasars pushes astronomy to ask deeper questions about how structure formed in the first place. Still, it is important not to imagine every black hole as a quasar machine. Most black holes are not producing quasar-like brilliance. Even many supermassive black holes are quiet most of the time. A quasar requires fuel. It needs a steady supply of matter moving inward. Galaxies can provide that fuel in different ways. Gas clouds may drift toward the center. Gravitational disturbances may rearrange matter. Sometimes galaxies interact or merge, stirring great streams of gas and pushing material inward. When enough matter begins to feed the central black hole, the region can become active and radiant. When the fuel supply falls away, the quasar fades. In that sense, a quasar is not an eternal object. It is a temporary state, though one that can last for immense spans of time by human standards. The radiation from a quasar does not come in only one kind of light. Quasars can emit across a wide range of the electromagnetic spectrum, from radio waves to visible light to X-rays and beyond. This broad emission tells us that the environment near the black hole is complex. Hot gas in the accretion disk glows intensely. Material closer in can reach even higher energies. In some quasars, narrow beams of matter and energy are launched outward at enormous speeds. So when astronomers study quasars, they do not rely on one window of light alone. They use many different kinds of telescopes to piece the object together. There is also a deeper reason quasars stay in the imagination. A quasar may be powered by a region far smaller than a galaxy, yet it can dominate the light of that galaxy. It may be so distant that its light began traveling toward us long before human history, yet it still arrives here, strong enough to be measured. Something invisible lies at the center, and yet the region around it becomes a beacon visible across the universe. And yet, once the mystery is unfolded, the core idea becomes surprisingly clear. A quasar is what happens when a supermassive black hole at the center of a galaxy is actively feeding on matter. The black hole itself remains dark, but the infalling material around it becomes so hot and energetic that it shines with extraordinary intensity. Because that light can overwhelm the surrounding stars, the galactic center can appear almost star-like from afar. Because many quasars are distant, they also let us look deep into the past. So a quasar is both a physical engine and a kind of time messenger, a natural laboratory where gravity, heat, motion, and cosmic history meet. That is what makes quasars feel so fundamental. They are not side characters in astronomy. They connect some of the biggest themes in modern science: black holes, galaxies, energy, time, and the evolution of the universe itself. To understand what a quasar really is, even at a basic level, is to understand that the cosmos can hide its greatest power in a point of light so small and distant that it almost looks ordinary. As the day begins to loosen its grip, you can let that thought settle gently in your mind. Somewhere in the deep dark, far beyond the reach of any road or morning, ancient light is still crossing space in silence. And for tonight, it is enough simply to drift with it. Chapter 2: How Astronomers First Discovered Quasars. The discovery of quasars began with a mystery so strange that for a time, astronomers were not even sure whether they were looking at stars, galaxies, or something the universe had never shown them before. In the middle of the 20th century, astronomy was changing quickly. For centuries, most of what humans knew about the sky had come through visible light. But then, radio astronomy began to reveal that the sky was full of sources that could not be understood by eye alone. Some objects that looked ordinary in visible light turned out to be powerful radio emitters. Others seemed to have no obvious visual counterpart at all. It was as if a second hidden sky had been uncovered behind the one people had always known. As astronomers mapped this radio sky, they noticed an important pattern. Many strong radio sources could be matched with galaxies, especially unusual galaxies with energetic centers or strange shapes. But not every radio source matched a galaxy. A few seemed to line up with what looked like faint stars. This was deeply confusing. Ordinary stars could produce radio waves, but not in the enormous amounts these sources seemed to be giving off. Something did not fit. One of the earliest and most important examples was a source cataloged as 3C48. It came from the third Cambridge Catalogue of Radio Sources, one of the major radio surveys of the sky. When astronomers matched the radio position of this source with a visible object, they found a faint blue point of light, star-like in appearance. If they had stopped there, it might have been filed away as some odd star. But when they took its spectrum, the object became a genuine puzzle. A spectrum is one of astronomy's most powerful tools. By spreading light into its component colors, astronomers can look for bright or dark lines linked to particular atoms. Those patterns act like fingerprints. They reveal what an object is made of and whether it is moving toward us or away from us. Usually, once a good spectrum is taken, the object begins to make sense. In the case of 3C48, the opposite happened. The spectrum showed broad emission lines in places that did not match anything familiar in a straightforward way. The object was clearly real, clearly energetic, and clearly unlike normal stars, but nobody could read its message with confidence. That was the first stage of the quasar story. Not discovery through understanding, but discovery through confusion. Astronomers had in front of them a new class of object, but they did not yet know it. They only knew that radio surveys were finding small, bright, star-like things that behaved in ways no ordinary star should. Part of the difficulty came from expectation. At the time, it was already accepted that distant galaxies existed far beyond the Milky Way. But the idea that a compact, nearly point-like object could sit at an enormous cosmological distance and still appear so bright seemed extreme. If these strange sources were truly very far away, then they would have to be unimaginably luminous. For many astronomers, that possibility felt almost too large to accept immediately. The breakthrough came through another radio source, one that would become famous, 3C273. Like 3C48, it had been detected as a strong radio emitter. But identifying its exact visible counterpart was not easy. Radio astronomy in those years did not always provide positions with the precision that optical astronomers wanted. A source could be located well enough to know roughly where it was, but not always well enough to say exactly which faint object in a crowded field was the correct one. That left room for error and occasional misidentification. A clever solution came from using the moon itself. When the moon passes in front of a distant radio source, the source disappears for a moment and then reappears. By timing that event very carefully, astronomers can determine the source's position in the sky much more accurately. This method, called lunar occultation, was used to sharpen the position of 3C273. That improved position pointed to a star-like optical object. Again, the visible object did not look like a galaxy in the ordinary sense. It looked more like a star. When its optical spectrum was studied closely, the result at first seemed just as baffling as before. There were bright emission lines, but they appeared in unexpected places. Then came the key insight. The lines were not unfamiliar after all. They were familiar hydrogen lines, but shifted strongly toward the red end of the spectrum. Once that possibility was recognized, the whole pattern snapped into place. This was the moment the mystery changed shape. The spectrum was not strange because the object contained unknown elements. It was strange because the known lines had been shifted by a large amount. In modern astronomy, such a shift is understood mainly as a sign that an object is very distant, and that the expansion of the universe has stretched its light to longer wavelengths while it traveled toward us. In other words, the object was not a nearby oddity. It was far away on a cosmic scale. That interpretation was revolutionary because it immediately transformed the object's true brightness. An object that looks modestly bright from Earth but lies at an enormous distance must be radiating staggering amounts of energy. 3C 273 was not a peculiar nearby star. It was an entirely different kind of source, one whose power exceeded anything expected from an ordinary star by an enormous margin. The same logic soon helped make sense of 3C48 and other puzzling sources as well. Once astronomers understood what they were seeing, the name followed naturally from the path of discovery. These objects had first appeared as star-like sources associated with radio emission, so they were described as quasi-stellar radio sources. Before long, that phrase was shortened into the word quasar. The name preserved the confusion of the first encounter. It described how the objects looked rather than what they were, because the word was born before the full physical explanation was known. The discovery of quasars was not a single isolated event, but a chain of progress in measurement and interpretation. Better radio surveys made the sources visible. Improved positions made optical matches possible. Spectra revealed that the visible counterparts were deeply unusual, and then one crucial act of recognition connected the evidence into a coherent picture. Once the redshift of 3C 273 was understood, many earlier clues suddenly made sense together. Even after that insight, acceptance was not completely instant. The distances implied by the redshifts were so large, and the luminosities implied by those distances were so extreme that some astronomers hesitated. Could the redshifts mean something else? Could these objects be nearby but governed by unfamiliar physics? Such questions were natural. Over time, however, more observations supported the distance interpretation. More quasars were found. More redshifts were measured. Their properties formed a pattern that was too consistent to dismiss. As the search widened, astronomers learned something else important. The first quasars had been found through radio surveys, but radio emission turned out not to be the defining property of the whole population. Many quasar-like objects were later found through their unusual blue color and their spectra rather than through strong radio signals. In visible light, they still looked almost stellar, but physically they belonged to the same broad family of extremely luminous active galactic nuclei. This mattered because it showed that the early radio-discovered quasars were only the beginning of a much larger population. That realization also changed how astronomers searched for them. Instead of relying only on radio catalogs, they began surveying the sky for blue star-like sources and then checking their spectra for the telltale shifted emission lines. In this way, discovery moved from rare accident to systematic method. Quasars changed from baffling outliers into a recognized category of cosmic object. The historical importance of this discovery is difficult to overstate. Quasars forced astronomers to confront the reality that the universe contains compact regions capable of producing enormous amounts of energy. They also showed that the distant universe was not quiet or simple. The farther astronomers looked, the more they found that the young cosmos contained brilliant active nuclei already shining across vast reaches of space. A faint point of light, barely distinguishable from a star on a photographic plate, could in truth be the active center of a galaxy billions of light years away. That lesson changed astronomy in a lasting way. It showed that the universe could hide its most dramatic structures behind appearances that seemed almost ordinary. Nature does not always announce its greatest discoveries with visual grandeur. Sometimes it reveals them through a spectrum that looks wrong, or through a radio source with no obvious identity, or through a small mismatch between expectation and measurement. So when we ask how astronomers first discovered quasars, the answer is not simply that they found a new object in the sky. They discovered quasars by learning to compare different kinds of light, by improving their measurements, by trusting spectral evidence, and by allowing the universe to be stranger than familiar categories had prepared them for. The path ran from radio astronomy to optical identification, from optical identification to spectral confusion, and from spectral confusion to the realization that these faint points were among the most luminous known objects in existence. And there is something quietly beautiful in that path. Long before astronomers understood what a quasar was physically, they were already receiving its light. The evidence had been arriving all along, crossing space in silence, waiting for human instruments and human thought to become precise enough to read it. Tonight, that old discovery can feel almost gentle, a reminder that even the deepest cosmic mysteries often begin as one small point of light, noticed carefully in the dark. Chapter 3. The Black Hole at the Heart of the Monster. At the center of every true quasar lies the same dark answer to its brightness. A black hole so massive that the light we see is really the sign of matter struggling in the grip of something we cannot see directly at all. This idea can sound almost backward at first. When people hear the phrase black hole, they usually imagine darkness, silence, and disappearance. When they hear the word quasar, they think of brilliance, distance, and overwhelming light. One sounds like absence, the other like excess. And yet the modern understanding of quasars depends on both at once. The bright monster is bright because of the dark object at its core. To understand why, it helps to begin with the black hole itself. A black hole is not a hole in the ordinary sense, like a tunnel or an empty cavity cut into space. It is a region where matter has been packed so densely and gravity has become so strong that once something crosses a certain boundary, it cannot come back out. That boundary is called the event horizon. It marks the point of no return. Outside it, matter and light may still escape if they have the right path and enough energy. Inside it, all future paths lead inward. The black hole itself does not shine because light that crosses the event horizon cannot escape to reach us. That is why a black hole is black, but black does not mean powerless. A black hole can still reveal itself through gravity. It can bend the paths of nearby stars, pull in gas, and reshape the motion of anything that comes too close. In astronomy, many invisible things are discovered not because we see them directly, but because we see what they do to everything around them. It is also important to clear away one popular misunderstanding. A black hole is not a cosmic vacuum cleaner that automatically swallows everything nearby. If the sun were somehow replaced by a black hole with the same mass, the planets would continue orbiting almost as before. The major difference would be that the sunlight would be gone. Gravity depends on mass and distance. From far away, a black hole pulls much like any other object of the same mass. What makes it special is how extreme gravity becomes when you get very close. Black holes come in different size ranges. Some form from the collapse of massive stars and contain a few times or tens of times the mass of the Sun. But the black holes that power quasars are in a different class altogether. They are supermassive black holes, the giants that sit in the centers of galaxies. These objects contain millions or even billions of times the Sun's mass. A quasar cannot be powered by an ordinary stellar black hole. The scale is far too large. When quasars were first discovered, their tremendous luminosity created a serious puzzle. The bright region appeared compact, yet it produced more energy than whole galaxies of stars. Astronomers had to ask what kind of engine could possibly do that. Over time, several lines of evidence converged on the same answer. The engine had to be small in size compared with a galaxy, but enormous in mass. It had to sit at the center of the host galaxy where the activity was observed. Supermassive black holes fit all of these requirements better than any alternative. One clue came from how quasar light changes. Many quasars vary in brightness over relatively short timescales. In astronomy, that matters greatly. If an object brightens or dims in a short period, the emitting region cannot be larger than the distance light can cross in that time. Otherwise, different parts of the object would not be able to coordinate their changes so quickly. This means the central engine of a quasar, though incredibly powerful, must also be compact. That combination is one of the great fingerprints of a black hole system. Enormous energy coming from a region far smaller than a full galaxy. Another clue came from nearby galaxies that are not quasars but still contain massive dark objects at their centers. Astronomers tracked the motions of stars and gas near galactic cores and found that they were orbiting something invisible and extremely massive in a very small volume. In our own galaxy, stars close to the central dark object move on tight, fast orbits that show beyond reasonable doubt that a supermassive black hole is there. This was a decisive step in black hole science. It showed that supermassive black holes are not speculative inventions made only to explain distant quasars. They are real components of galaxies. Once that became clear, the next idea followed naturally. If many galaxies contain central supermassive black holes, then a quasar can be understood as a galaxy whose central black hole is in an active phase. The black hole is there whether the galaxy looks dramatic or quiet. What changes is whether enough matter is falling inward to create a blazing nucleus. In a calm galaxy, the central black hole may sit in relative darkness, affecting nearby stars through gravity, but producing little radiation. In a quasar, the same kind of object is actively being fed. So the black hole at the heart of a quasar is not some exotic object unrelated to the rest of the universe. It belongs to a population that seems to be common in large galaxies. What makes the quasar special is not the mere existence of the black hole, but the extreme conditions around it. The monster wakes up when fuel arrives. There's still a natural question here. If black holes are dark, how can astronomers be so confident that one sits inside a quasar if the center is flooded with light? The answer is that the light itself behaves exactly as expected if matter were orbiting and falling toward a supermassive black hole. The motions are rapid, the energies are extreme, the source is compact. In some active galaxies, material near the center moves at enormous speeds under the influence of a huge gravitational field. The broadening of spectral lines, the timing of brightness changes, and the concentration of energy all point to the same underlying structure. There are also direct images of the environments around supermassive black holes in some nearby galaxies, showing glowing rings of material and a dark central shadow. These images do not come from quasars themselves, which are often much farther away, but they strengthen the larger case. They show that supermassive black holes are real physical objects with the expected effects on surrounding matter and light. At the deepest level, the black hole in a quasar is defined by gravity, not by brightness. Gravity shapes the paths of matter and light around it. Gravity sets the speed of orbiting gas. Gravity determines how close material can come before crossing the event horizon forever. The black hole does not need to glow in order to dominate. Its power lies in what it makes other matter do. The event horizon is central to this picture because it marks the true border of the black hole. Outside that boundary, matter may still orbit, heat up, collide, and release radiation that escapes into space and eventually reaches Earth. Once matter passes inside, however, it is gone from the visible universe. For an outside observer, the event horizon is the last meaningful edge. Everything we can study directly in a quasar happens outside it, in the surrounding environment, shaped by its presence. What lies deeper still is one of the places where known physics reaches its limit. According to general relativity, matter collapsing inside a black hole continues inward toward a singularity, a state where density and curvature become extreme in ways the theory itself cannot fully handle. Most physicists take this as a sign that our current theories are incomplete under such conditions, not as a final picture we completely understand. So when speaking carefully, astronomers are most confident about the event horizon and the powerful gravitational field around it. That uncertainty does not weaken the black hole explanation for quasars. Astronomers do not need to know every detail of the interior to identify the central engine. They can infer the mass from orbits, compactness from variability, and the presence of infalling matter from radiation. Piece by piece, the hidden object reveals itself through the structure it imposes on the surrounding region. There is something almost elegant about this. A quasar appears at first to be a monument to light, but its true center is a place from which no light escapes. The brightest galactic nuclei are built around invisible gravity wells. What we admire from across the universe is not the black hole itself, but the drama it creates just outside its boundary. This is why the phrase "the black hole at the heart of the monster" is more than poetic. It is literal. Without the black hole, there is no quasar in the full sense. But the sustained, concentrated, galaxy outshining engine of a quasar requires a supermassive black hole at the center. It is the anchor of the whole phenomenon. And yet, for all its extremity, the idea is not beyond imagination. A quasar is not magic. It is gravity working on a vast scale. It is matter responding to one of nature's deepest rules. At the center is a black hole, silent and unseen. Around it, the universe announces that hidden presence in heat, motion, and light. By learning to read those signs, astronomers found the darkness inside the brightness. As this chapter settles, you can let the image become a quiet one. Far away, in the heart of a distant galaxy, there is a region darker than anything the eye could see, and around that darkness, the universe slowly writes its circle of light. For tonight, you do not have to solve it. You can simply rest with the thought that even the brightest monsters are built around stillness. Chapter 4. How falling matter creates so much light. If the black hole is the hidden center of a quasar, then the great puzzle of the quasar is not the darkness itself, but the astonishing brightness that appears just outside it. How can falling matter, which sounds passive and final, become one of the most luminous processes in the universe? The answer begins with gravity, but it does not end there. A quasar shines so intensely because matter falling toward a supermassive black hole does not simply drop straight in and vanish. Instead, it becomes trapped in motion, squeezed by gravity, heated by friction, and transformed into radiation before it disappears. That process is easier to understand if we start with a simple idea. In everyday life, falling can release energy. A rock dropped from a height strikes the ground with force because gravity has accelerated it. Water falling downhill can drive a turbine and produce electricity. In each case, gravitational energy is being converted into motion, and that motion can then be turned into heat or useful work. A quasar works on the same basic principle, but on a scale so extreme that the result becomes cosmic. Matter near a supermassive black hole is rarely motionless. Gas clouds in a galaxy are already orbiting the galactic center. Dust is drifting, stars are moving, and streams of material may be pushed inward by collisions, gravitational disturbances, or galactic mergers. Because this infalling matter already has sideways motion, it usually cannot plunge directly into the black hole. Instead, it begins to circle it. This is a crucial point. The path inward is not a straight fall. It is a spiral. That spiral creates what astronomers call an accretion disk, a flattened rotating structure made of gas and dust orbiting the black hole. It is not a solid surface like a planet's disk or a record on a table. It is a vast flow of material, with different parts moving at different speeds. The material closer to the black hole must orbit faster than the material farther out, because gravity is stronger there. So the disk is a place of constant internal shear. Inner layers race ahead, while outer layers lag behind. When different layers of gas move at different speeds, they rub, twist, and stir one another. Not like solid sandpaper, but through turbulence, collisions between particles, and the behavior of magnetic fields threaded through the hot plasma. This internal struggle matters enormously. It is what allows the disk to evolve. If every bit of matter simply orbited peacefully forever, then it would never move inward, and the quasar would never be powered. Something has to drain orbital energy from the gas and redistribute its angular momentum so that part of the material can spiral inward while other parts carry momentum outward. This is one of the deepest ideas in the physics of accretion. To fall inward, matter must get rid of some of the motion that keeps it in orbit. The disk itself provides the mechanism. Through turbulence and magnetic stresses, angular momentum is transported outward. That lets some gas move closer to the black hole. As it does so, gravity pulls it into faster orbits and deeper regions of the gravitational well. More orbital energy is lost, more heat is generated, more radiation is produced. The disk is not merely a storage ring around the black hole. It is an engine for turning orbital motion and gravitational energy into light. This is why the material heats up so dramatically. The gas in the disk is compressed and stirred as it spirals inward. Tiny particle interactions repeated on an enormous scale convert organized orbital motion into random thermal motion. In plain language, the gas gets hot because the orderly movement of circling matter is being broken down and redistributed. The closer the gas moves to the black hole, the more intense this process becomes. That is why the inner parts of an accretion disk are hotter and brighter than the outer parts. The temperature structure of the disk shapes the light it produces. Farther from the black hole, where conditions are less extreme, the disk may emit longer wavelength radiation such as visible or infrared light. Closer in, where the gas becomes much hotter, it emits ultraviolet light and even higher energy radiation. So when astronomers study a quasar, they are not looking at a single uniform glow. They are seeing the combined radiation from many zones of the disk, each one heated to a different degree by its distance from the center and by the violence of the orbital flow. This is also why a quasar can outshine an entire galaxy. It is not because the black hole itself emits light. It is because the region around the black hole is extraordinarily efficient at converting the energy of infalling matter into radiation. In ordinary stars, light comes from nuclear fusion in the core. In quasars, much of the visible power comes from the gravitational energy released as matter spirals inward. For sustained luminosity from a compact region, this is one of the most efficient mechanisms known in nature. A relatively modest amount of matter, fed steadily into such a system, can produce an astonishing amount of light. It may help to imagine the accretion disk as a descending whirlpool of fire, though even that image is too gentle. In a whirlpool on Earth, water spirals inward under gravity and loses height. In a quasar, gas spirals inward under gravity and loses gravitational energy. But instead of splashing quietly into a drain, it is heated to extraordinary temperatures while still orbiting at enormous speeds. The closer it gets to the center, the more severe the transformation becomes. There is another important feature near the black hole. Matter does not keep circling forever. There comes a point where stable circular orbits are no longer possible. Outside that region, gas can orbit while slowly losing energy and drifting inward. Inside it, the motion changes. Matter plunges more directly toward the event horizon. By the time gas reaches this inner zone, much of the radiative work has already been done. The brightest light mostly comes from the disk before the material finally crosses the point of no return. Around the inner disk, there is often an even hotter, thinner region, sometimes called the corona. This is not a corona like the atmosphere of the sun in a simple sense, but a cloud of extremely energetic particles above and around the disk. Radiation from the disk can pass through this hot environment and be boosted to higher energies. That helps explain why quasars emit not only visible light and ultraviolet light, but also X-rays. So the total brightness of a quasar is a layered phenomenon. The disk produces a broad glow of thermal radiation, while the hotter surrounding regions can add more energetic emission. Not all the energy stays near the black hole either. Some of the heated material can be driven outward in winds. In certain quasars, magnetic fields and rotation help launch narrow jets of matter away from the center at enormous speeds. These jets can travel vast distances into intergalactic space. They are dramatic and important, but they are not the main reason the quasar is bright in the first place. The central light comes primarily from the hot accretion flow itself. The jets are another expression of the same deep engine, not the engine's main light source. One reason this process can continue for so long is that the black hole does not need to devour everything all at once. As long as fresh gas is supplied to the central region of the galaxy, the accretion disk can remain active. Some periods may be brighter than others. If more matter arrives, the quasar can flare. If the fuel thins out, the light can fade. In that sense, the quasar is not a permanent lamp, but a feeding state. Its brightness reflects how much matter is being supplied and how effectively that matter is being converted into radiation as it spirals inward. There is also a kind of balance involved. If too much energy is released outward as radiation, that light can push back on the infalling gas. Radiation pressure can oppose gravity, especially in the inner regions. So the system is not simply a one-way collapse. It is a dynamic contest between inward pull and outward pressure, between supply and feedback, between flow and resistance. Real accretion disks are not perfectly smooth. They flicker, churn, heat unevenly, and respond to changing conditions. This helps explain why quasars can vary in brightness over time. What makes all of this so remarkable is that the source of the light is not combustion, and not ordinary starlight, and not a giant explosion. It is controlled release. Gravity brings the matter inward. Orbital motion prevents a direct plunge. The disk forms. Turbulence and magnetic stresses gradually remove angular momentum. The gas spirals closer. The deeper it falls, the hotter it becomes. The hotter it becomes, the more intensely it radiates. By the time the matter is finally lost to the black hole, a great deal of its accessible energy has already been poured into the universe as light. This is why quasars are such profound objects in astrophysics. They show that falling can shine. They reveal that darkness can produce brilliance, not by emitting it directly, but by forcing surrounding matter into one of the most extreme energy conversion processes nature allows. A quasar is not bright despite the black hole at its center. It is bright because the black hole's gravity creates the conditions under which falling matter is heated, stressed, and illuminated. And this gives the quasar its strange emotional quality as well. It is a place where loss becomes radiance. Matter moves inward toward disappearance, yet before it vanishes, it lights up the cosmos. A galaxy can carry this brilliant wound at its center, a place where gravity does not merely destroy but also reveals. So when we ask how falling matter creates so much light, the answer is no longer mysterious, even if it remains awe-inspiring. Matter near a supermassive black hole forms a disk because it carries angular momentum. The disk's inner and outer parts move at different speeds, which creates turbulence and magnetic stress. Those processes let some material lose angular momentum and spiral inward. As it falls deeper into the gravitational field, gravitational energy is converted into heat. The heat makes the gas radiate across many parts of the electromagnetic spectrum. The closer the matter comes, the more intense the conditions become, until finally the inner flow passes beyond the last stable orbits and disappears across the event horizon. The light we see is the final brilliance of matter on its way down. And as that idea settles into place, it can become strangely peaceful. Across the deep universe, ancient gas is still circling invisible centers, warming as it descends, glowing before it is gone. You do not need to hold the whole mechanism in your mind now. You can let it soften into one quiet image, a slow spiral of light around darkness, turning in silence far beyond the day you are leaving behind. Chapter 5. Jets, Radiation, and the Violence Around Quasars. A quasar is not only a bright center in a distant galaxy, it is also one of the most extreme environments known in astronomy, a place where light, plasma, magnetic fields, and fast-moving gas interact so intensely that a tiny point of light in the sky hides a region of continual upheaval. From very far away, a quasar can look simple, almost still. But the closer astronomers study it, the more complicated the central region becomes. Around the supermassive black hole, there is not just an accretion disk. There is also a hot corona, clouds of ionized gas, dust farther out, powerful winds, and in some cases, narrow jets of plasma launched outward along the system's rotation axis at speeds approaching the speed of light. The glow of the quasar is only one part of the story. The word violence is useful here if it is understood scientifically. It does not mean intention or emotion. It means that energy is being transferred rapidly. Matter is being accelerated to enormous speeds, and radiation is being produced at levels far beyond anything familiar on Earth. A quasar is violent because gravity and electromagnetism are pushing matter into states that are hot, fast, and unstable. The radiation from a quasar spans much more than visible light. The central engine can emit radio waves, infrared light, visible light, ultraviolet light, X-rays, and in some cases even gamma rays. That wide output tells astronomers that a quasar is not made of one single glowing layer. Different regions produce different kinds of radiation. Dust farther out glows mostly at longer wavelengths. The hot inner disk radiates strongly in visible and ultraviolet light. The corona above and around the disk can produce higher energy X-rays. And the jets, when present, and especially when aimed close to our line of sight, can generate radiation across much of the spectrum. The corona is one of the strangest parts of the system. It is thought to be a very hot region of energetic particles located above and below the accretion disk. Its exact shape is still being studied, but its basic role is clear enough. Light emerging from the disk can pass through this cloud of energetic particles and gain energy through repeated interactions. In that process, lower energy photons can be boosted into X-rays. This is one reason quasars are strong X-ray sources. Beyond the immediate disk and corona, there are clouds of gas moving under the influence of the central engine. Some of these clouds orbit close enough to the center that they move at enormous speeds. Their motion broadens the spectral lines they produce, which is why many quasars show very wide emission features when their light is spread into a spectrum. Farther out, other gas clouds move more slowly and produce narrower lines. Even the detailed shape of a quasar's spectrum reveals motion, showing that the central region is not quiet or uniform, but filled with gas responding to strong gravity and intense radiation. That radiation does not simply stream outward passively. It changes the matter around it. Gas near a quasar can be ionized, meaning its atoms have had electrons stripped away by energetic photons. Strong radiation can heat clouds and help drive outflows away from the center. In some quasars, astronomers see clear evidence that gas is not only falling inward to feed the black hole, but also being pushed outward at high speed. These outflows can take the form of broad winds from the accretion disk, carrying energy and matter into the host galaxy. This brings us to the jets, which are among the most dramatic structures associated with quasars. Not every quasar produces large, easily detected jets, but some do, and when they appear, they can extend far beyond the galaxy itself. A jet is not a beam of light in the simple sense. It is a narrow outflow of plasma, meaning matter in which electrons and nuclei are no longer bound into ordinary atoms. This plasma is guided and accelerated by powerful magnetic fields connected to the rotating disk and, very likely, to the spin of the black hole itself. The result is a pair of oppositely directed streams shooting away from the central region along the poles of the system. The broad physical picture behind these jets is now persuasive, even though some details remain under active study. Near the black hole, magnetic fields become twisted by the rotation of the disk and the extreme conditions of the inner region. Under the right conditions, those fields can channel energy outward and collimate matter into narrow beams. Instead of gas moving in all directions, the magnetic structure helps organize part of the flow into long, thin jets. These jets can remain astonishingly straight over immense distances, which is one reason they are so striking in radio images. The plasma in a jet does not move slowly. In many cases, it travels at speeds very close to the speed of light. When a jet is pointed somewhat toward Earth, this creates important observational effects. The radiation can appear boosted and more variable because of the jet's motion. This is why some active galactic nuclei look especially bright and erratic when one jet happens to be aimed nearly in our direction. In that viewing geometry, astronomers often classify the object as a blazar. A blazar is not a different engine in the deepest sense. It is largely a matter of orientation and jet dominance. Orientation matters for quasars more generally as well. The central black hole, disk, corona, gas clouds, dusty outer structure, winds, and jets may all be present in related forms, but their apparent prominence changes with viewing angle. If dust and gas obscure our direct view of the center, the quasar may appear altered at certain wavelengths. If the jet points close to us, the object may look unusually intense in radio waves, X-rays, or gamma rays. If the system is tilted another way, the jet may be less obvious, while the disk and line-emitting gas dominate what we observe. The jets are also powerful particle accelerators. Electrons spiraling through magnetic fields in the jet emit synchrotron radiation, which is a major source of radio emission and can also contribute at higher energies. In the most extreme cases, particles in or near the jet can produce gamma rays as well. This means that a quasar is not only a luminous object, but also a natural laboratory for physics under conditions impossible to reproduce on Earth. Far from the center, the jets can slam into surrounding gas and continue feeding giant radio lobes on either side of the galaxy. These extended structures show that the influence of the quasar does not end near the black hole or even near the visible body of the host galaxy. Energy launched from the central engine can travel outward for enormous distances, heating gas, stirring matter, and changing the larger galactic environment. And jets are only one form of outflow. Quasars can also drive broad winds from the accretion disk, and these winds may carry a great deal of mass and momentum. In some systems, high-speed winds revealed in X-ray or ultraviolet observations suggest that the disk is shedding matter while still feeding the black hole. These winds can collide with colder gas in the host galaxy and help push it outward. Over long periods, such feedback may influence how much gas remains available for future star formation. This combination of inward feeding and outward attack is what makes the quasar environment so remarkable. The black hole grows by pulling matter inward, but the process of growth can generate enough light, heat, wind, and jet power to push matter back outward. The central engine feeds and resists at the same time. The radiation itself can be dangerous in a very literal sense. Near the quasar, high-energy photons can strip electrons from atoms heat matter to extreme temperatures, and make the environment hostile to stable structures. Any ordinary planetary system too close to the active nucleus would be exposed to radiation fields far beyond what life as we know it could tolerate. Still, for all this activity, the quasar is not random. Its violence has structure. The disk lies mostly in one plane. The jets emerge along the poles. The corona occupies the central hot region. Gas clouds orbit at different distances. Dust obscures and re-radiates. Radiation pressure and magnetic fields help shape outflows. Each part responds to the same hidden engine, and together they form a system that can be studied and understood. So when we speak of jets, radiation, and the violence around quasars, we are describing the outer expression of gravity working through matter and fields. The black hole itself remains dark. The brightness, the X-rays, the ionized gas, the winds, the radio emission, the gamma rays, and the polar jets all belong to the environment built around that darkness. A quasar is not just a bright center. It is an organized storm around an invisible core. As this chapter settles, you can let the picture soften. Far away, beyond the reach of any ordinary night, two thin streams of plasma may still be crossing the dark between galaxies while the center that launched them burns in many kinds of light at once. You do not need to follow every photon now. You can simply imagine the distant engine turning in silence and let the day loosen its hold. Chapter 6. Why Quasars Live So Far Away in Time. When astronomers say that quasars live far away in time, they do not mean that these objects belong to a separate universe or to some strange hidden dimension. They mean something both simpler and more profound. Light takes time to travel. Because the universe is so vast, seeing something far away also means seeing it as it was long ago. A nearby tree is seen almost now. The moon is seen a little in the past. A star is seen years in the past. A quasar, because it is often extraordinarily distant, is seen in a much deeper past, from an age when the universe itself was younger than it is today. This is one of the most beautiful ideas in astronomy because it forces us to stop thinking of the sky as a single moment spread above us. The night sky is not a picture taken all at once. It is a layered record of different times. Every object we see is sending us old light, and the age of that light depends on distance. The farther away the source, the longer its light has been traveling. In that sense, telescopes are not only instruments for seeing far away, they are instruments for seeing backward. Quasars are especially important in this picture because they are so luminous. Many distant galaxies are too faint to stand out clearly at the greatest reaches of the observable universe, especially in older surveys. Quasars, by contrast, can shine with such intensity that they remain visible across immense cosmic distances. That makes them natural beacons from the deep past. Their brightness allows them to announce themselves across stretches of space so large that by the time their light reaches us, the universe has changed enormously. So the first reason quasars seem to live far away in time is observational. They are bright enough to be seen from very far away, and far away means long ago. Even before we ask why the early universe produced so many of them, we have to understand this basic fact. Quasars are among the best distant signposts available to astronomers. There is also an important difference between distance in space and distance in time. In everyday life, those two ideas feel separate. A city can be far away, but it still exists at the same moment as we do. In cosmology, the two ideas become linked because information cannot travel instantly. We never see distant objects as they are right now in some absolute sense. We see them as they were when the light left them. If a quasar is billions of light years away, then the image we receive today began its journey billions of years ago. The quasar may look entirely different now. It may have faded, changed state, or become quiet. What reaches us is the record of an earlier chapter in its life. The expansion of the universe adds another layer to this story. Light traveling across cosmic distances does not move through a static stage. Space itself expands while the light is on its way. As that happens, the light is stretched to longer wavelengths. This effect is called cosmological redshift. It is one of the main reasons distant quasars look the way they do in spectra. Their light has not only traveled for an immense time, it has also been carried across an expanding universe that has changed the light during the journey. The larger the redshift in general, the farther away the object is, and the earlier in cosmic history we are observing it. But this still leaves the deeper question. If quasars are visible from far away because they are bright, why do so many of the known and famous ones belong to earlier cosmic eras? Why do quasars seem to crowd the remote universe more than the nearby one? The answer lies in how galaxies and black holes change over time. A quasar is a phase of intense feeding around a supermassive black hole. For that phase to happen, large amounts of gas must reach the central region of a galaxy and remain available for accretion. In the early universe, galaxies were generally richer in cold gas than many large galaxies are today. They were still assembling much of their structure. Star formation was more active on average. Interactions and mergers between galaxies were also more common. All of this created conditions in which gas could be driven inward more often, feeding central black holes and turning galactic nuclei into brilliant engines. In other words, the young universe was a busier place. Galaxies were still growing, colliding, rearranging themselves, and consuming large reservoirs of gas. A supermassive black hole sitting in the center of such an environment had a better chance of being fed at a high rate. And when that happened, the galaxy could enter its quasar phase. Over time, many galaxies used up or lost much of the easy fuel that once fed both stars and central black holes. Gas was turned into stars. Some of it was blown outward by stellar explosions, galactic winds, or activity from the central black hole itself. Some settled into more stable orbits that did not easily send it inward. As galaxies aged, the most extreme feeding events became less common on average. Supermassive black holes did not disappear, but many became quieter because the conditions that produce quasar-level luminosity were no longer as common. This is why quasars are not evenly spread across cosmic history. They have an era of abundance, a broad period when black hole growth and galaxy growth were both especially active. Astronomers sometimes describe this as a kind of high noon in cosmic history, when the universe was particularly productive in building stars, feeding black holes, and shaping the large galaxies we know today. When we look out to those distances, we are looking back into that more energetic age. The nearby universe, by comparison, is calmer. There are still active galactic nuclei in the modern universe. Some nearby galaxies contain bright nuclei, jets, or strong radiation from feeding black holes. A few true quasars are relatively close in cosmic terms, but they are rarer than they were in the past. The great age of quasar abundance lies behind us. and because of light travel time, we can still observe it shining in the distance. This leads to an important subtlety. Quasars do not literally live in the past, as though time were a place where they remain trapped. Rather, we see many quasars in the deep past because that is when quasar activity was more common, and because their luminosity allows them to be seen across those distances. The phrase is poetic, but the science behind it is precise. We are looking outward into space and therefore backward into history, and the history we find contains more bright quasars than the recent universe does. There is also a selection effect hidden inside this picture. Extremely distant astronomy always favors the brightest objects. A faint, active nucleus in the far universe may be too difficult to detect, while a luminous quasar can stand out. So part of the reason distant catalogs contain so many quasars is that quasars are the members of the active black hole family, most able to announce themselves across the largest distances. This does not create the whole pattern, because quasar activity truly was more common in the past, but it strengthens what we notice. Quasars also illuminate more than themselves. Their light passes through gas between galaxies on its way to Earth. That gas leaves absorption features in the spectrum, allowing astronomers to study the material spread across intergalactic space. In this way, a quasar acts like a flashlight shining through the universe. Because many quasars are so distant, they help reveal what the intervening cosmos was like at earlier times. The farther back we see a quasar, the younger the universe in that image. That means quasars can help astronomers trace how black holes grew, how galaxies evolved, and how matter was distributed through different eras. A distant quasar is therefore not merely a remote light source. It is a timestamp. It tells us that by that point in cosmic history, a galaxy had already formed. A supermassive black hole was already present, and enough matter had already reached the center to ignite an active nucleus of enormous power. It is also worth remembering that the quasar itself is temporary. A galaxy may not remain in that state forever. It can brighten when fuel arrives and dim when the feeding slows. So when we look at a distant quasar, we are seeing not only a distant object, but a temporary phase captured in transit. Some distant galaxies that blaze in the sky as quasars may, by the current age of the universe, have settled into quieter lives. So the answer to this chapter's question has two parts that belong together. Quasars live far away in time because they are so bright that we can see them across immense distances. And immense distances mean large look-back times. But they also seem especially tied to the deep past because the earlier universe provided richer conditions for feeding supermassive black holes. Young galaxies held more gas, underwent more interactions, and more often entered powerful active phases. The sky preserves that era for us. When we look far enough, we do not merely see more space. We see an age when quasars were more at home. And as the idea settles, it can become a gentle one. Somewhere beyond the stars of our own galaxy, light is still arriving from a time when the universe was younger, fuller, and more restless than the one around you now. You do not need to chase it any farther tonight. It is enough to know that the dark above you is also a memory, and that some of its oldest lights are only reaching you now. Chapter 7. Quasars in the Young Universe. When astronomers find a quasar in the young universe, they are not just finding a bright object at a great distance. They are finding evidence that very early in cosmic history, nature had already built something enormous, hungry, and unexpectedly mature. That is what makes early quasars so important. In the nearby universe, a quasar is already an extreme object. But in the young universe, it becomes something more than extreme. It becomes a puzzle. The reason is simple to state, even if it is difficult to solve. A quasar requires a supermassive black hole feeding at a powerful rate. Yet the earliest known quasars appear at times when the universe was still very young. Somehow, in what seems like a very short cosmic interval, matter had to gather, collapse, form galaxies, produce central black holes, and then grow some of those black holes to extraordinary size. To understand why this is surprising, it helps to imagine the early universe not as a finished star field, but as a place still assembling itself. After the hot beginning, the universe expanded and cooled. Matter was not evenly spread. Tiny differences in density present from the beginning allowed gravity to slowly amplify structure. Regions that were slightly denser than average pulled in more matter. Over time, these denser regions became the first halos of dark matter and gas, the frameworks within which the first stars and galaxies began to form. The earliest galaxies were not usually calm, settled systems like many large galaxies today. They were smaller, richer in gas, and more chaotic. Star formation could be intense. Mergers and inflows were more common. The whole universe was younger, denser, and more active. These conditions made early galaxies fertile ground for black hole growth. But even then, the brightest early quasars seem almost too developed, as though the cosmos had moved faster than astronomers expected. This is why early quasars sit at the center of one of the great questions in astrophysics. How did supermassive black holes grow so large so quickly? The problem is not that growth is impossible. It is that the earliest luminous quasars seem to require either very large starting seeds, very rapid feeding, or both. Astronomers use the word seed for the first black hole from which later growth begins. One possibility is that some of the earliest massive stars ended their lives by collapsing into black holes. These stellar remnants could then begin accreting gas and merging with other black holes over time. That idea is attractive because it starts from processes already expected in early star formation. But there is a difficulty. If the initial seeds were relatively modest, then growing them into the enormous black holes required by the earliest bright quasars may be hard unless the feeding is extremely efficient and sustained. A different possibility is that some early black hole seeds were born already much larger. In certain regions of the young universe, under the right conditions, a dense cloud of gas may have collapsed directly into a massive black hole instead of first breaking into ordinary stars. This idea is often called direct collapse. It would give the universe a head start. Instead of beginning with a stellar remnant and slowly building upward, nature would begin with a much heavier seed already in place. There are also hybrid possibilities. A black hole might begin as a stellar remnant, then grow through a mixture of gas accretion, mergers with other black holes, and episodes of especially rapid feeding. The truth may not be a single pathway. The young universe may have produced black holes through more than one channel, depending on local conditions in gas, radiation, and structure formation. What makes the puzzle especially rich is that the brightest early quasars are not the whole story. For a long time, the distant quasars easiest to detect were the most luminous ones, which meant astronomers were seeing the giant, highly active end of the population. Those objects were so bright that they stood out strongly even from the early universe. But they may not have been typical. More recent observations have started to uncover smaller active black holes at great distances as well, revealing a fuller range of early growth stages. That is important because it helps bridge the gap between theoretical seeds and the fully developed luminous quasars that first drew attention. In that sense, the young universe may have hosted not only brilliant quasars, but also a broader ecosystem of growing black holes. Some would have been modest and still building. Some may have been heavily obscured by gas and dust. Some would have been in short-lived rapid growth phases. The most luminous quasars are the dramatic peaks of this hidden population, but not the whole landscape. Early quasars also matter because they lived during one of the most important transitions in cosmic history, the era when the gas between galaxies changed from mostly neutral to mostly ionized. In the young universe, much of intergalactic space was filled with neutral hydrogen. Neutral hydrogen is very good at absorbing certain kinds of energetic light, which made the universe much less transparent than it is today. As the first stars, galaxies, and black holes formed, they began producing radiation that altered this gas. Over time, more and more of the intergalactic medium became ionized, and the universe became more transparent. This transformation is often called reionization, and early quasars are valuable guides to it. Their light travels through the gas between galaxies before reaching us. Along the way, that gas leaves traces in the quasar spectrum. By studying those traces, astronomers can learn about the state of the intergalactic medium in different eras. A young quasar therefore does two jobs at once. It is itself an object of deep interest, and it is also a flashlight shining through the early universe, revealing what lies between us and it. At first glance, it might seem that quasars could have been the main agents responsible for reionizing the universe. After all, they are enormously bright and emit powerful radiation. But the current picture suggests that ordinary early galaxies, especially numerous faint ones, were probably the main drivers of this transition. Quasars likely contributed in some regions and at some times, but they do not seem numerous enough to explain the entire process on their own. Even so, they remain essential witnesses to the event. Their light helps measure it, even if their total contribution to causing it was limited compared with the vast collective output of young galaxies. There is another reason early quasars are so revealing. They do not appear randomly across the early universe. The brightest among them seem to prefer dense environments, regions where matter was gathering efficiently and where future large-scale structures were beginning to take shape. When astronomers study the galaxies surrounding some early quasars, they often find hints that these objects sit in unusually rich neighborhoods. That makes sense. To build a powerful quasar early, the universe likely needed a place where gas, dark matter, and galactic interactions were all unusually favorable. So an early quasar is not only a story about one black hole. It is also a clue about its environment. It points to a region where structure formation was running ahead, where galaxies were clustering, where matter was flowing inward, and where the central black hole had access to fuel. In this way, early quasars help map the architecture of the young universe. The black hole at the center of such a quasar is also not acting alone in shaping its host galaxy. Even at these early times, active black holes may have been driving winds and outflows that influenced how gas moved through the galaxy. If a black hole feeds vigorously, the resulting radiation and outflows can heat or expel some of the gas that would otherwise form new stars. This means early quasars are not just passengers in young galaxies. They may be participants in shaping them. That idea is important because it suggests that galaxy growth and black hole growth were linked from very early on. The host galaxy helps feed the black hole, and the active black hole pushes back on the galaxy. This partnership, sometimes cooperative and sometimes destructive, may have been established surprisingly early in cosmic history. What continues to make early quasars so compelling is that they combine direct observation with unresolved theory. Astronomers do not doubt that these distant quasars exist. Their spectra, luminosities, and host environments have been observed in increasing detail. The uncertainty lies in the path that led to them. Did nature form unusually massive seeds? Did some black holes spend long periods feeding at rates faster than the usual radiation-limited pace? Did frequent mergers help accelerate growth? Was the early universe simply better at assembling massive black holes than older models assumed? The answer may involve several of these ideas at once. In a way, early quasars are records of accelerated cosmic history. They show us that the young universe was capable of organizing matter into powerful, compact engines far sooner than once seemed likely. They remind us that the first billion years of cosmic time were not slow or empty. They were productive, restless, and filled with rapid change. Galaxies were assembling, stars were forming, gas was moving, the intergalactic medium was transforming, and in the middle of all that, some black holes were already becoming giants. So when we speak of quasars in the young universe, we are speaking about more than distant lights. We are speaking about the first great black hole growth era, about the early shaping of galaxies, about the changing state of the space between galaxies, and about one of the clearest signs that the young cosmos was both creative and surprisingly efficient. The earliest quasars are among the strongest reminders that the universe did not spend its youth waiting quietly to become interesting. It became interesting very quickly, and as this chapter comes to rest, the image can soften again. Somewhere in the deep past, long before the Earth existed, a young galaxy was already feeding a dark center until it blazed across the early universe. That ancient light is still arriving now, gentle by the time it reaches you, carrying news from a restless age into the quiet of your evening. Chapter 8. How Quasars Shape Their Galaxies. A quasar does not simply sit inside a galaxy like a lamp in a room. When a galaxy enters a quasar phase, the energy released near its central black hole can begin to change the galaxy itself, stirring its gas, altering its future, and linking the fate of the small central engine to the much larger system around it. At first, that idea sounds almost impossible. The galaxy is enormous. It contains stars, gas, dust, dark matter, and structures spread across distances so large that light itself needs many thousands of years to cross them. By contrast, the region immediately around the black hole is tiny compared with the full galaxy. So how could something happening in such a small central zone influence the whole system? The answer is energy. A quasar concentrates an extraordinary amount of energy into a compact space, and that energy does not remain politely confined. It emerges as radiation, winds, and in some cases jets, and these outputs can interact with the galaxy far beyond the center. This broad process is often called feedback. In ordinary language, feedback means that an effect circles back and influences its own cause. In the case of quasars, the black hole grows by feeding on matter from the galaxy, but the act of feeding releases so much energy that it can change the galaxy's gas supply. That means the black hole does not simply consume what the galaxy gives it. It can also heat, disturb, or expel the very material from which both future stars and future black hole growth would otherwise arise. To understand why this matters, it helps to remember what galaxies need in order to make stars. Stars form from gas, especially cold, dense gas that can collapse under its own gravity. If a galaxy has plenty of such gas, it can remain actively star-forming. If the gas is heated, dispersed, or removed, star formation becomes more difficult. In this sense, the future of a galaxy depends strongly on the condition of its gas. A quasar can influence that condition in several ways. One way is through radiation itself. A quasar emits intense light across much of the electromagnetic spectrum. That radiation can heat surrounding gas, ionize it, and increase the pressure in the interstellar medium. Gas that is hotter is usually harder to collapse into new stars. If the quasar remains active long enough, it can help keep parts of the galaxy's gas reservoir in a state that is less friendly to star formation. Radiation alone does not always blow all the gas away, but it can change the balance of temperature and pressure inside the host galaxy. Another way is through winds. Quasars can drive large-scale outflows of gas away from the central region. These winds may begin near the accretion disk, where radiation pressure and other forces accelerate matter outward. As they move through the galaxy, they can sweep up additional gas and carry mass, momentum, and energy into the surrounding medium. If enough gas is pushed out of the dense central regions, then less material remains available for star formation there. In some cases, observations show outflows moving fast enough and carrying enough mass that they appear capable of clearing or thinning the gas in the host galaxy. Jets can also play a major role, though not every quasar shows them in the same way. A powerful jet does not merely shine. It punches into surrounding gas, heating it, shocking it, and in some environments, inflating cavities or lobes. Even when a jet does not directly sweep gas out of the galaxy, it can inject energy into the galactic or surrounding medium, helping prevent gas from cooling and settling into the dense clouds needed for new stars. In that sense, feedback is not always a dramatic one-time blow. Sometimes it is more like long-term interference with the galaxy's ability to recycle its gas into fresh star formation. This idea has become important in modern galaxy evolution because astronomers have long faced a puzzle. If galaxies simply kept cooling their gas and turning it into stars without interruption, many of the most massive galaxies in the universe would become even more overgrown than they actually are. Yet many large galaxies today are relatively quiet, filled mostly with older stars and producing few new ones. Something seems to regulate their growth. Quasar feedback is one of the leading explanations for how that regulation happens, especially during earlier, more active phases of galaxy evolution. There is observational support for this picture. Astronomers have detected quasar-driven outflows in gas around host galaxies, and in some systems, have found evidence that regions affected by these outflows show reduced star formation. One well-known result showed a powerful outflow associated with a distant quasar and indications that the molecular gas needed for star formation had been strongly depleted in the affected region. This does not prove that every quasar always shuts down star formation in the same way, but it does show that such suppression can happen in real galaxies. Even so, the story is not perfectly simple. Quasars do not always act as pure destroyers of star formation. In some circumstances, the pressure of an outflow or jet can compress gas clouds rather than dispersing them. Compressed gas can sometimes become denser and more likely to collapse, which means feedback may briefly trigger or enhance star formation in particular regions. Current reviews suggest that this kind of positive effect can occur locally, even while the larger overall effect of feedback is still to reduce the availability of gas and suppress star formation across broader scales. So a quasar may both kindle and extinguish, depending on where you look and on what time scale. This is one reason astronomers are careful with their wording. It would be too simple to say that quasars merely turn galaxies off. In some galaxies, feedback may primarily heat gas. In others, it may drive large-scale outflows. In others still, it may create a mixed pattern. Local compression and temporary star formation along the edges of expanding structures, while the galaxy as a whole loses cold gas and trends toward quiescence. The physics is real, but the exact outcome depends on the mass of the galaxy, the amount and distribution of its gas, the geometry of the outflow, the presence or absence of jets, and how long the central engine remains active. There is another clue that quasars and galaxies are linked more deeply than a simple one-way attack. The masses of supermassive black holes are observed to correlate with properties of their host galaxies, including the mass of the central stellar bulge and related measures of galactic structure. These relationships do not, by themselves, prove the detailed mechanism of feedback, but they strongly suggest that black hole growth and galaxy growth are connected over long periods of cosmic time. It is difficult to believe that the central black hole and the galaxy evolved entirely independently if their properties track each other so closely. This is where the idea of coevolution becomes useful. The galaxy feeds its central black hole by delivering gas inward. The black hole responds by releasing energy through its active nucleus. That energy can then reshape the gas supply in the galaxy, affecting both future star formation and future black hole feeding. Over many cycles, the galaxy and black hole may regulate one another. The galaxy helps build the black hole, and the black hole helps determine what kind of galaxy will remain afterward. In this view, a quasar phase may be one of the great transition moments in a galaxy's life. A gas-rich galaxy can spend time making stars rapidly while also feeding its central black hole. As the black hole becomes more active, the resulting feedback may begin to clear, heat, or disturb the gas. The galaxy then shifts toward a quieter future, with lower star formation and a more dormant central nucleus. It is not that the quasar destroys the galaxy. Rather, it may help transform a youthful, gas-rich galaxy into a more mature and passive one. This also helps explain why quasars matter far beyond their brilliant central light. If they were only spectacular curiosities, they would still be worth studying, but they seem to participate in one of the biggest patterns in cosmic history: the gradual emergence of the galaxy population we see today. Some galaxies remain active and star-forming for long periods. Others become redder, older, and quieter. The activity of supermassive black holes appears to be one of the processes helping guide those paths, especially in the most massive systems. It is also important to note that feedback does not need to remove every last bit of gas to matter. Sometimes simply heating gas enough to prevent it from cooling efficiently is already enough to slow future star formation. In a galaxy, the key question is not only how much gas exists, but whether it can settle into the cold, dense state required to form stars. A quasar can therefore shape its galaxy not only by dramatic expulsion, but also by changing the thermal and dynamical life of the gas that remains. And because quasar phases are temporary, their influence can echo after the brightest stage is gone. A galaxy may no longer look like a quasar host, yet still bear the consequences of earlier feedback in its gas content, star formation history, and central black hole mass. In that sense, many quiet galaxies may carry the after effects of ancient active phases that helped shape the systems we see today. This idea fits naturally with the evidence that supermassive black holes are widespread in large galaxies, and that many of those galaxies likely passed through more active phases earlier in cosmic time. So when we ask how quasars shape their galaxies, the answer is not a single dramatic mechanism, but a relationship. Quasars release immense energy into their host galaxies through radiation, winds, and sometimes jets. That energy can heat gas, push gas outward, prevent cooling, and reduce the raw material available for future stars. In some places, it may also compress gas and briefly trigger star formation, even while the larger effect tends toward regulation or suppression. Through these processes, the central black hole and the host galaxy become linked in a long history of mutual influence. The quasar is not just something inside the galaxy. It is part of how the galaxy becomes what it is. As this chapter settles, you can let the scale of it become quiet instead of overwhelming. A small, bright center in a distant galaxy can send its influence outward through gas and starlight, slowly changing a system far larger than itself. And somewhere in the dark, many galaxies may already be carrying the memory of such an episode, shaped long ago by a brilliant core that has since gone still. Chapter 9. How we study quasars today. Today, astronomers study quasars by treating them not as single points of light, but as layered physical systems whose distance, mass, motion, environment, and history can all be teased out from the different kinds of light they send across the universe. The most basic step is still finding them in the first place, but even that has become far more sophisticated than it once was. Modern surveys scan huge areas of the sky and compare how objects appear in different wavelengths of light. Quasars often stand out because they are unusually bright, unusually blue or red in certain bands, or because their spectra show the shifted emission lines that reveal both their nature and their distance. Large observing programs now gather spectra for enormous numbers of galaxies and quasars, turning quasar discovery from a rare event into a systematic scientific enterprise. Spectroscopy remains one of the central tools. When astronomers spread a quasar's light into a spectrum, they are not just admiring a rainbow. They are measuring fingerprints of atoms, temperatures, motions, and cosmic expansion. The positions of emission lines help determine redshift and therefore distance. The widths of those lines reveal that gas near the center is moving at tremendous speeds. The relative strengths of different lines provide clues about the density, temperature, and ionization state of gas surrounding the black hole. In many ways, spectroscopy is how quasars stop being mysteries and begin to become physical systems. Astronomers also study quasars across the full electromagnetic spectrum because no single kind of light tells the whole story. Visible and ultraviolet light help trace the accretion disk. X-rays probe hotter and more energetic regions close to the central engine. Radio observations reveal jets and extended lobes when those are present. Infrared light can uncover dust, hidden structure, and in some cases quasars whose centers are partly obscured. A modern understanding of a quasar usually comes from combining several observatories, each sensitive to a different part of the spectrum, into one coherent picture. This multi-wavelength approach matters because quasars are not simple light bulbs. The radiation we receive can come from different regions with different temperatures and different physical processes. If astronomers relied only on visible light, they would miss much of the story. X-rays can reveal energetic processes very close to the black hole. Radio waves can map the shape and reach of jets. Infrared observations can peer through dust and show how the central engine affects the surrounding galaxy. Each window adds a piece, and only together do they show the quasar as a full structure rather than a bright blur. Imaging is another essential tool, though it is more challenging for quasars than for many other cosmic objects. The bright central light can overwhelm the host galaxy that surrounds it, making the quasar look almost star-like even in powerful telescopes. To overcome this, astronomers use high-resolution space telescopes and careful image analysis to separate the dazzling nucleus from the fainter galaxy around it. This is how they study quasar host galaxies. Ask whether the host is a spiral or an elliptical system, look for signs of mergers, and learn what kinds of galaxies are capable of feeding such powerful central engines. Sometimes the surrounding galaxy is not the only faint thing astronomers want to uncover. In the early universe, quasars can act like beacons that illuminate nearby galaxies and gas structures too dim to find easily on their own. Infrared-sensitive instruments can study the regions around distant quasars and reveal how those quasars sit inside larger environments of forming galaxies. In that way, a quasar can be used not only as an object of study but also as a signpost for locating especially interesting parts of the young universe. Time is another tool. Quasars vary. Their brightness can rise or fall over days, months, years, and longer timescales. Astronomers do not treat this variability as a nuisance. They use it. Because different parts of the quasar respond on different timescales, changes in light can reveal the structure of regions too small and distant to image directly. Repeated observations let scientists measure how the quasar brightens, dims, and echoes through its own gas, which turns time into a kind of ruler. One of the most important techniques built on this idea is reverberation mapping. In simple terms, astronomers watch for a change in the quasar's continuum light from the accretion region and then measure how long it takes for surrounding gas clouds to respond. That delay gives an estimate of the distance between the central light source and the line-emitting gas. Combined with the observed speed of the gas, it allows astronomers to estimate the mass of the central black hole. This is one of the cleverest methods in modern astronomy because it extracts size and mass information from timing rather than direct imaging. Radio astronomy provides a different kind of access. With large radio arrays and very long baseline techniques, astronomers can resolve fine structure in jets and compact radio cores that would be impossible to see otherwise. Radio observations reveal how plasma is launched, how jets stay narrow over great distances, and how they interact with the surrounding galaxy or intergalactic medium. In some cases, radio time-lapse observations can even show apparent motion in jet features, giving insight into relativistic outflows and the geometry of the system. X-ray astronomy probes, still closer to the center. Quasars can be powerful X-ray sources, and that radiation often comes from regions near the innermost parts of the accretion flow. By analyzing X-ray spectra, astronomers can infer how hot the central environment is, how matter is distributed, and in some cases, even estimate black hole spin. Spin matters because it carries information about how the black hole has grown over time, whether mainly by steady accretion, mergers, or some combination of both. X-rays therefore help connect the immediate physics of the quasar to the long history of its central black hole. Sometimes, nature provides an extra advantage through gravitational lensing. If a massive galaxy lies between Earth and a more distant quasar, gravity from the foreground galaxy can bend and magnify the quasar's light, producing multiple images or boosting features that would otherwise be too faint to study well. Astronomers use these lensed quasars as natural experiments. The separate light paths can reveal time delays, small-scale structure, and in some cases allow especially detailed study of the central regions. Gravitational lensing can therefore turn the universe itself into part of the observing instrument. Quasars are also studied through the gas that lies between them and us. As their light travels across intergalactic space, it passes through clouds and halos of gas that absorb specific wavelengths. Those absorption features leave patterns in the spectrum, allowing astronomers to study matter that would otherwise remain nearly invisible. This means a quasar can serve as a backlight for the universe. By reading the shadows imprinted on its light, scientists investigate the composition, temperature, motion, and distribution of gas across cosmic distances. Millimeter and submillimeter observatories add yet another layer by tracing cold gas and dust in quasar host galaxies. These observations are especially valuable when astronomers want to know how much raw material for star formation remains in the host, whether gas is being blown outward, and how the black hole is interacting with its wider galactic environment. In some distant quasar hosts, these instruments have even revealed strong molecular outflows, showing that the central engine can affect the galaxy's star-forming fuel directly. There are also cases where quasars are useful beyond quasar science itself. Because they are so distant, their positions on the sky are effectively fixed for many practical purposes. For that reason, catalogs of quasars are used to help define celestial reference frames, giving astronomy a stable background against which the motions of nearer objects can be measured. In a quiet way, quasars help anchor our map of the sky. What makes quasar research today especially powerful is not one telescope or one method, but coordination. Astronomers combine survey data, spectra, time variability, radio maps, X-ray measurements, infrared imaging, and sometimes gravitational lensing into one layered interpretation. A quasar may first be noticed in a large survey, then confirmed by spectroscopy, then monitored over time, then imaged with a space telescope, then examined in X-rays or radio waves, and finally placed in the context of its host galaxy and cosmic environment. Modern quasar science is therefore not a single observation but an assembled portrait built from many kinds of evidence. And that is perhaps the most remarkable part of all. Quasars are among the most distant and brilliant objects known, yet astronomers have learned to measure their redshifts, estimate the masses of their black holes, map their jets, study their host galaxies, use their flickering as a ruler, and even use them as background lamps for the universe itself. We do not touch them, and we do not travel to them, but by learning to read light in all its forms, we have turned these remote monsters into knowable systems. As this chapter comes to rest, you can let that thought become a calm one. Somewhere very far away, a quasar is still shining through darkness, and here in a much smaller and quieter place, human beings have learned to understand it by collecting its light patiently, piece by piece. That may be one of the gentlest triumphs in science. Not conquering distance, but listening to it carefully enough that even the farthest fires begin to speak. Chapter 10. What Quasars Reveal About the Universe. A quasar is easy to describe as a bright object, but that description is far too small for what it truly gives to science. Because quasars have become some of the universe's most powerful messengers, revealing how black holes grow, how galaxies evolve, how the early cosmos changed, and how light itself can carry the history of space across unimaginable distances. A quasar is never only about itself. It is not merely a distant engine, not merely a feeding black hole, and not merely a spectacle. It is an instrument provided by nature. When astronomers observe one, they are not learning just about one galaxy's nucleus. They are learning about a chain of deeper truths that reach far beyond that single source of light. One of the first and most important things quasars reveal is that supermassive black holes are not rare accidents. They appear to be woven deeply into the life of galaxies. The modern picture is no longer that galaxies are collections of stars that sometimes happen to contain an unusual central object. Instead, many galaxies seem to grow alongside a central black hole, and in at least some phases of their lives, that black hole can become active enough to dominate the galaxy's appearance. Quasars helped force this realization. Before them, a black hole at a galactic center might have seemed like a theoretical curiosity. After them, it became part of the basic architecture of the cosmos. Quasars also reveal something profound about gravity. In ordinary human experience, gravity feels gentle. It pulls rain downward, keeps the moon in orbit, and holds us to Earth. In a quasar, gravity shows another face. It becomes a power source. It can take matter that is falling inward and turn that motion into heat and radiation on a scale large enough to outshine billions of stars. This teaches a wider lesson about the universe. The same laws that govern familiar things can, under extreme conditions, produce phenomena that seem almost unbelievable. They also reveal that darkness and light are not always opposites in the way we imagine. A quasar is built around something that does not shine at all. The black hole itself remains dark, yet the region around it can become one of the brightest known in the universe. This is not only a dramatic image, it is a scientific lesson in indirect knowledge. Much of astronomy depends on learning about invisible things through their effects. We infer black holes through motion, lensing, heating, and radiation. Quasars are among the clearest examples of that method. Another major revelation concerns time. Quasars teach, with unusual force, that looking into space is looking into history. All astronomy carries this truth, but quasars make it vivid because they can be seen across such enormous distances. Their light often began traveling toward us when the universe was far younger than it is now. So a quasar is not only an object, but also a timestamp. It tells us that by a certain early era, galaxies had already formed, black holes had already grown, and the cosmos had already become capable of building compact engines of astonishing power. In that way, quasars reveal that the young universe was not empty and immature for very long. It organized itself quickly. This has led to one of the deepest open questions in modern astrophysics. If the earliest bright quasars already contained enormous black holes, how did those black holes grow so rapidly? Quasars do not yet give a complete answer, but they define the problem with stunning clarity. They tell us that the first billion years of cosmic history were more productive than older, simpler pictures once suggested. The young universe was building galaxies, igniting stars, shaping intergalactic gas, and somehow creating giant black holes all at once. Quasars also reveal that galaxies and black holes are connected in a two-way relationship. A galaxy supplies matter to its center. The central black hole feeds. In feeding, it releases radiation, winds, and sometimes jets. Those outputs then act back on the galaxy, heating gas, stirring it, and in some cases reducing the raw material available for later star formation. This means a quasar is not just a sign that a black hole is growing. It is also evidence that the black hole may be helping shape the future of the host galaxy. That relationship matters because galaxies are among the universe's main structural units. To understand why some galaxies keep making stars while others grow quieter, why some remain gas-rich while others become more passive, and why the largest galaxies do not keep forming stars without limit, astronomers need to understand the role of black hole feedback. Quasars reveal that the central regions of galaxies are not just endpoints where matter disappears. They are active participants in cosmic evolution. Quasars further reveal that the space between galaxies is not empty in any simple sense. As quasar light crosses the universe, it passes through gas spread through intergalactic space. That gas leaves signatures on the light in the form of absorption features. By reading those signatures, astronomers have learned that the universe is filled with diffuse matter, distributed in filaments, clouds, halos, and large-scale structures. Quasars therefore act like backlights for the cosmos. This becomes especially important when studying the era of reionization, the time when the gas between galaxies changed from mostly neutral to mostly ionized. Quasars did not seem to be the main agents driving that transition, yet their spectra provide some of the clearest evidence for what the intergalactic medium was like near the end of that era. Through quasars, astronomers can study how transparent the universe had become at different times, and how the first generations of luminous objects were transforming cosmic gas. They also reveal something about cosmic structure on the largest scales. The brightest early quasars tend to mark regions where matter was gathering efficiently and where galaxies were likely assembling into denser environments. A distant quasar can therefore signal a region of the young universe that was developing unusually quickly. In this way, quasars help trace the growth of the cosmic web, the vast network of matter from which galaxies and clusters emerge. There is also a methodological lesson hidden in quasar science. Quasars reveal how much can be learned from light alone. Human beings cannot travel to them. We cannot place instruments beside them. We cannot sample their gas directly. Yet by collecting photons across the electromagnetic spectrum, by tracking changes over time, by measuring spectral line widths, by using gravitational lensing, and by comparing many observations at once, astronomers can estimate black hole masses, study jets, map environments, and probe cosmic history. They show that careful observation, repeated patiently and interpreted through physical law, can turn distant points of light into richly understood systems. They reveal, too, that the universe is layered rather than simple. A quasar may seem at first like one bright source, but it contains many nested realities. There is the central black hole, the accretion flow, the high-energy corona, the line-emitting gas, the dusty outer regions, the host galaxy, the intergalactic medium between it and us, and the cosmological expansion affecting the light on its journey. To study a quasar is to encounter astronomy at many scales at once, from the behavior of particles in hot plasma to the growth of structure across the universe. For that reason, quasars also reveal something about the character of scientific progress. They were first discovered as strange point-like sources that defied familiar categories. Only gradually did their meaning become clear. Since then, each generation of telescopes has turned them into sharper tools and deeper puzzles. New observations have not erased the mystery. They have refined it. That is often how science moves forward. Perhaps the deepest lesson quasars reveal is that the universe is not built on a comfortable scale. Some of its decisive processes happen in places too far away to imagine easily, around objects too dense to see directly, over intervals too vast for ordinary intuition, and with energies beyond everyday comparison. Yet the same universe also allows those remote processes to become knowable. A species on one small planet can detect the light of a quasar, decode its spectrum, estimate the mass of its hidden center, and use it to reconstruct the state of the universe billions of years ago. So in the end, what do quasars reveal about the universe? They reveal that black holes are central to galaxy history. They reveal that gravity can be a supreme maker of light. They reveal that the early universe grew structure quickly, and perhaps more efficiently than we once assumed. They reveal that galaxies and their central engines co-evolve. They reveal the otherwise hidden gas between galaxies. They reveal stages in the universe's changing transparency. They reveal the large-scale structure of matter. And they reveal that light, if read carefully enough, becomes a record not only of distant objects, but of cosmic history itself. As the last part of this story grows quiet, you can let quasars become what they have always been for us. Ancient lights crossing a dark ocean of space, carrying news from a universe that was younger, rougher, and more brilliant than the one around you now. You do not need to solve every mystery they bring. It is enough for tonight to know that some of the brightest monsters in existence have helped us see the larger shape of the darkness around them. And now, my friend, our journey through the light of quasars comes to a quiet end. If you're still awake, you might enjoy drifting into another video and letting the universe carry you a little farther. But if sleep is finally close, then let this final thought stay with you. Somewhere out in the dark, ancient light is still crossing space in silence. Thank you for spending this time here with me. Sweet dreams among the stars.